Ladies and gentlemen, please welcome to stage Jingguang Cheng, President of NACS.
How do I turn it on? Oh, there we go. So, good morning. Welcome on behalf of the Society, North American Catalytic Society. Welcome to NAM 28. I think we're going to have a very excellent program. Hope you enjoyed the firework last night. So I also like to use this opportunity to really thank the New England Catalysis Club and also Meeting Solutions for putting together a really great program. So now it's my pleasure to introduce the co-chairs. I will call them to be recognized on stage. Steve Soup and Chris Landry. And also we have a third co-chair, Scott Auerbach, who cannot be here today due to some other reasons. And now it's my greatest honor to introduce the honorary chair, Gary Heller. Please stand up to be recognized. So. And now I'll yield the floor to Chris to start the program. So, Chris, go ahead.
Thank you, Jingguang. I'm Chris Landry from the University of Vermont. I'm one of the co-chairs for this year's conference. I just want to say how gratifying it is to be here with you. So thank you for your energy, for your attendance, and looking forward to a great week. I hope you enjoyed the opening ceremonies last night. Looking forward to a great week of discussion. And it's my first order of business to talk a little bit about housekeeping. So if I could have the first slide. Just talking a little bit about emergency procedures. So you can see the evacuation locations. It was actually effectively leading to a service corridor behind me and then out to the parking garage should we need it. So just be aware of that in the event of an emergency. And then, next slide, please. We wanted to, on the organizing committee, put an emphasis on wellness for this conference. So along those lines, just remember to take care of yourself. And if you're not feeling well, consider wearing a mask. And for those who are not COVID positive, masks are optional. And there's other things going on this week that I wanted to point out. I am actually teaching a yoga class. It's on the social events, 5:45, so I expect to see you all there in the Omni. I have the mats, so there's no excuse. There's also Fun Run this week. You'll find a route in Providence on the social events page. And just check out the social events and enjoy your time in Providence. And moving on, there's a QR code which I would encourage you to scan right now that will lead to the code of conduct for the conference. It's another point that we had a lot of discussions about on the organizing committee. So it's important to us that everyone feels, is respected, included, and safe. So no verbal or physical harassment. Just be careful of your communications and your behavior during the conference, and of course, no recording of presentations. And many of you are also aware, I hope, that today is Juneteenth, which is a national holiday that is celebrating the emancipation of African American slaves in the United States. And again, we had a lot of discussion about this and the organizing committee. And I think, in thinking about racism, it's important to not only be thinking backwards in remembrance and in celebration, but also in thinking forward in terms of action. So to paraphrase Angela Davis, it's not enough to just not be a racist. We have to actively be anti-racist. So along these lines, the organizing committee would like to invite all of you to take a moment of silence right now to recognize Juneteenth. Thank you. And this is a good opportunity to pivot to mention the DEI luncheon, which is happening tomorrow. So if you're interested in continuing this discussion, there's tickets still available for the DEI lunch, which is here in the convention center. So you can register at the registration desk outside if you're interested in the DEI lunch. And next, I just wanted to take a moment to give a big thank you to our rhodium sponsor, I would say the first rhodium sponsor of NAMM conferences, and that is Shell. So thanks very much. A conference like this is not possible without sponsors at that level, and we really appreciate and are grateful for their support. And of course, I want to say a big thank you to other sponsors at the gold level, the silver level, and even at the bronze level, including some academic sponsors as well as industrial ones. Thank you for all of your support as well. And the next order of business is to introduce the Paul Emmett Award in Fundamental Catalysis for 2023. And first, a little bit about Paul Emmett. He was in the chemical engineering department at Johns Hopkins until his retirement. Those of us who work with porous materials are familiar with the BET method of surface area investigation, and he co-developed that method, obviously, Braunauer, Emmett, and Teller. And that paper still is one of the most cited in the physical sciences. And if we look at the list of awardees, you can see it's a lot of people who've had a lot of influence in our field, all the way up through last year. And so this year's awardee is Aditya Bhan. And with that, I will turn to Matt Nurak, who will introduce today's speaker. Thank you.
Well, good morning, everyone. I want to start by congratulating Gary as well as Aditya and Yuri on, at least for Yuri and Aditya, for two very well-deserved awards. They've really had a remarkable impact on the field in terms of what they've done. And so it's my great pleasure and delight to be here today to introduce Professor Aditya Bhan. Aditya received his BS degree from IIT Kanpur in 2000, his PhD from Purdue, working with Nick Delgas in 2005, and then he did a postdoc with Enrique Iglesias from 2005 to 2007. And that's where I first met Aditya. He's doing really some outstanding pioneering work on carbonylation that has made it up to industrial process and practice level. And so it was great. He came out to my lab for a while, and so I really enjoyed and followed his career ever since. He then went on in 2007 to start at the University of Minnesota in the Department of Chemical Engineering, and he shot up through the ranks there, and about 2 months ago was awarded one of the highest awards that we have at the university, Distinguished McKnight University Professorship. Aditya has also been a guest professor at ETH in Zurich, as well as a visiting scientist, and he's worked many, many years now with Dow Chemical on various different technology. Aditya has really pioneered seminal advances in understanding and elucidating what are the active sites, what are the elementary steps, what are the kinetics and the mechanisms that control selective hydrocarbon conversion processes, really for the production of fuels and chemicals in these systems for materials, microporous materials, as well as metals, metal oxides, metal carbide materials. And he's done so by integrating and seamlessly integrating rigorous and transient as well as steady state kinetics, along with isotopic labeling, in situ titration, temporal co-feed experiments, and the list goes on, in situ spectroscopy, along with modeling and theory, really to tease out and understand what's the nature of the active site, what are the kinetics for that site and the mechanism, and stitch that all together into the pathways for very complex reaction systems, and showing the influence of catalyst surface structure, composition, and confinement effects that drive these reactions. He's established very elegantly the role of transport in these systems and deactivation for many problems, industrial problems, to where deactivation is very significant. In addition to this, he loves mathematics, and so in the past few years now, he's established a novel mathematical approach to analytically solve for the issue that we have with Langmuir-Hinchelwood models, where you've got coverage effects and different species interact with one another. And this pioneering work has really set us well into the future to be able to model such systems. So his rigor and depth are really unparalleled in the field. He's made a number of advances in different areas. I don't have the time to go into them, but I'll just pick one to highlight really his work on methanol, the hydrocarbons. He's probably one of the pioneering leaders in that field, making tremendous advances with the rigorous kinetics that he's done to understand olefin cycles, aromatic cycles, how they communicate specifically to one another, and how one can change zeolite topology, crystallite size, silica to alumina ratio, and co-feed other species to give you specific selectivity to products. He was one of the first to show that formaldehyde is the key problem child, is it kicks off really the mechanisms that lead to deactivation, and more importantly, showed ways in which we can reduce that by adding hydrogen, water to these systems, or yttria to basically diminish the role of what formaldehyde would do and eliminate it. He's had tremendous advances in a number of other areas, methane dehydroaromatization to aromatics, as well as work in partial oxidation of different hydrocarbon intermediates. Due to his research, he's won a number of amazing awards, a Young Scientist Award from the Acid and Base community, the Richard Glenn Award for Energy and Fuels, ACS, the Aditya Prize from ACS, as well as Young Career Awards from DOE, as well as NSF, and a wide range of other awards, truly very well deserved. In addition to this, he's an exceptional teacher, and he's won a number of awards at the University of Minnesota for his efforts in the classroom, both at the undergrad level as well as at the graduate level. He's been just a devoted servant of the field, working countless hours really to help advance on many, many committees, organizing many conferences and symposium. He's been an editor for the Journal of Catalysis for the past 6 years. And he served in leadership roles across the community as the chair of ACS, Catalysis Science Technology Division, as well as the director of Catalysis and Reaction Engineering for AICHE. Most importantly, and probably one of his major advances, is really he's an exceptional mentor. He's produced 25 PhD students, 13 postdocs, all phenomenal, and due to the fact that he works very closely with them, and they all, he's just a wonderful mentor and colleague as well. And so you can see that in the number of his students past students who are here at the meeting, and the success that they've had in industry as well as academia. Last but certainly not least, he's just a wonderful colleague and friend and an exceptional individual. He's across the hall from me, and he's listened countless times where I'll come wandering in with scientific questions or concerns, and so he's almost like a son, but in terms of age, but he acts like a father or a brother. And so please join me in congratulating Aditya and welcome him to the stage.
Thank you for the very kind introduction, Matt. That's going to be hard to follow. Please let me start by acknowledging the organizers of NAM 28 for organizing the meeting, to the North American Catalysis Society for this honor. I'm very grateful, humbled, surprised, and honored to be here. Thank you very much. To W.R. Grace for sponsoring this award. And perhaps let me again start by acknowledging the people who, while standing here, how I've gotten to this point. Perhaps nobody is more responsible for the fact that I'm standing here than the person whose teachings and examples stand before me today as they did since 2000. We lost Nick on 17th August 2021, but for those of you who knew Nick, how much joy he got out of this job, how enthralled he was with every aspect of this job, of teaching, classroom teaching, of working with students, of presentations. It's an example that I have to follow today. It'll be one that will stay with me for the rest of my life. I was very fortunate to have Nick as an advisor, and his loss is felt today as well. No one has taught me more in science than Enrique Iglesias, whose group I went for a postdoc, either in my postdoc or since then. But all of you know Enrique as a scientist, and I wish a few more of you knew him as a mentor. There's no better example of that than myself. Somewhere in the middle of my postdoc, I decided that academia was too difficult for me. I was never going to get an academic position. And without his infinite patience, support, to get me through that phase, I would not be standing here. So recognize him for the scientist that he is, the amazing scientist, but please also recognize him for the amazing mentor that he is to his students. And as I said, there's no better example of that than myself. We've been very fortunate to have support over the year from industrial sponsors, as well as a number of, particularly from the Department of Energy, the National Science Foundation. This has allowed us to do our work. The three that I've highlighted above have been long-term supporters. It's been really amazing to have their support. It's been wonderful to work with Dow over many years. It has gotten us, broadened our scientific scope, given us opportunity to work on new problems. I'm grateful for that. I am the tremendous beneficiary of a supportive and collegial department. Not only one where I learned with a history in mathematics or in chemical reaction engineering, where I have colleagues as brilliant as Matt Newrock, who I get to talk with almost every day. Almost every day, Matt and I sit and talk about something in science. It's really amazing to have that opportunity to discuss. Paul Downhauer, who can tweet a storm like nobody else that I know, but he also brings an excitement and an optimism in science which is infectious. It's a department where I learned early on that awards are not the narrative in science. Awards are at best punctuation marks in the narrative, a brief respite from what we do, perhaps a cause for celebration, but they're not the narrative. The narrative for us academics is the science that we do and the people that we work with. So let me tell you about the narrative in our group. And again, I'm delighted to be here to represent them to you. This is who we are. I am privileged to stand here in front of you to be a representative of this group and nothing more. This remains my highest privilege and my greatest honor to work with these students. So this is who we are. There are 14 of them in the audience. If you see them, please congratulate them as well. This is who we are. This is what we do. I took this quote. I promised to tell you something about what maddens and torments us in C1 conversion. This is a quote from Moby Dick. Let me read it to you, and then I'll discuss the chemistry. All that most maddens and torments, all that stirs up the lees of things, all truth with malice in it, all that cracks the sinews and cakes the brain, all the demonisms of life and thought. No malice, hopefully truth. I'm going to tell you about two chemistries that have been of interest to us. One, concerning methanol to hydrocarbons, where my goal will be to control the kinetic trajectory, prevent it from going towards deactivating side paths. Okay? And the second, where my goal will be to control the thermodynamic trajectory of the reaction, because I have thermodynamic restrictions on here. So in one, I'll focus on the kinetics. The other one, the thermodynamic trajectory. Let me pick up the first one. These are both well-known chemistries. I'll introduce them only briefly. But the first chemistry that is of interest to us, one we worked on for many years, is methanol to hydrocarbons. This is already practiced on an industrial scale. It's practiced widely because you can take any carbon feedstock, essentially, convert it to methanol as a platform, and then this methanol can be converted to fuels, can be converted to chemicals, very versatile chemical platform. It's selective in making certain hydrocarbons. That is already an accomplishment, and this is why it's practiced industrially. What torments us about this chemistry is that the catalyst deactivates. In this case, this is run in very complex reactors with riser fluid bed reactors because the catalyst deactivates. And I'm not going to talk to you about any engineering, but I am going to talk to you about the chemistry that happens in here in the pores of the zeolite. Why does it deactivate? What chemistry? There are many ways to deactivation. I'll highlight one which is specific to methanol and how we went about addressing that challenge. How should you think about methanol to hydrocarbons chemistry? It's a solid acid catalyst. It's a zeolite. You should think about this catalysis as a polymerization reaction. It's akin to, for example, a polystyrene or making polystyrene. You have an initiation step which initiates some chain carriers. You have a propagation step where you have successive chain growth. And you have a termination step where you either add a cation or you essentially run out of the reagent, an initiation, a propagation, and a termination. Very similarly, in methanol to olefins, you should think about a zeolite, a solid acid. In this case, I'm showing you a schematic for chabazite-type zeolites. This is the industrial zeolite that's used for methanol to olefins. It has these cages which are quite large and these windows which allows molecules to come in. Some rare event, either an impurity or some rare event, initiates the reaction. You have organic species which are essentially circumscribed inside the zeolite pore. These are the catalytic centers. This is what initiates, this is what propagates the reaction. You make CC bonds reacting with these organics, and you break CC bonds. This is the propagation cycle. And ultimately, you terminate to make polycyclic aromatics. So that's what I'll focus on for most of the talk, but let me talk about the propagation cycle. This is what is known as the hydrocarbon pool mechanism, and we had a precedent literature to follow on before we came into the field, and there are two important things to keep in mind. There's many details here, but there are two important things to keep in mind. Those organics that can be trapped inside the zeolite can be of two kinds. They can be either olefinic, you successively methylate, make larger and larger hydrocarbons that can crack, or you make aromatics that can methylate, make larger and larger aromatics that can dealkylate and make olefins again, and these two cycles talk to each other. So simply for us to keep in mind, there are two types of organic species that can be inside the zeolite pores, olefins or aromatics. And the other thing to keep in mind in this chemistry, following again detailed isotopic work, which showed that the ethylene is a product of the aromatic cycle. The isotopic distribution of ethylene is very similar to that of all the aromatics and different from all the other olefins. So I will use ethylene as a marker for propagation of the aromatic cycle. And we were the beneficiaries of a tremendous amount of literature from Topsoe, from the University of Oslo, to do this work. We already had this insight before going into the problem, and then we started our work. So two cycles, aromatics and olefins, and ethylene as a marker for the aromatic cycle. And when we started our work, this is a medium pore zeolite. This is MF5. This has about 5.5 angstrom pores. The first question we wanted to answer was, if we want to change the selectivity in methanol to hydrocarbons, in this zeolite is quite simple because this zeolite allows communication with the gas phase. These hydrocarbons can leave these medium pore zeolites, and you can communicate with the gas phase. In this case, I can change the composition of the hydrocarbon pool by simply changing the composition of the gas phase because I can communicate with the gas phase. So if I take dimethyl ether, this is the dehydration product of methanol. If I take dimethyl ether and I feed propylene, I get a certain product distribution. I get a fair amount of C4 to C7 hydrocarbons. If I feed dimethyl ether and toluene to propagate the aromatic cycle, I don't make so many C4, C7, and I can very systematically vary the composition of the hydrocarbon pool by changing what's in the gas phase. And that allows me to tune selectivity in methanol to hydrocarbons because I have this handle of changing the composition of the gas phase. To change the composition of the hydrocarbon pool, I don't only have to change things in the gas phase, I can also change something about the zeolite. Let me change the crystallite size. Okay, this is a material property. If I change the crystallite size, I see very systematic trends in ethylene selectivity. The aromatic cycle propagates more. I told you the aromatic cycle, the marker for the aromatic cycle is ethylene. Why is that so? In this is a diffusion-limited chemistry. Essentially, what I've done is I've changed the intracrystalline contact time. How much time does a molecule spend within a crystallite? As I change the crystallite size, the aromatic cycle, which is more likely to be diffusion-limited, has a higher intracrystalline residence time. And I propagate that cycle more, I get a systematic trend in ethylene selectivity. I get more olefins, and this is because I've changed the intracrystalline residence time. I don't have to do this only by changing the crystallite size. I can also change the silicon to aluminum ratio, again, another material characteristic. I can change the silicon to aluminum ratio, and now what I'm changing is not the intracrystalline residence time, but the intracrystalline contact time. How many protons do I encounter before I leave a crystallite? I see, again, a very systematic trend in light olefin selectivity, particularly ethylene. How many protons do I encounter before I leave a site? This is something we have to keep in mind when we work with diffusion-limited systems. Again, the cycle that's more likely to be diffusion-limited experiences this more, and I get a very systematic trend in selectivity, and that's due to the intracrystalline contact time. I can combine all these parameters. I can take this proton density, crystallite size. I get a very systematic trend in selectivity. These are not good or bad MTO or MTH catalysts. These are diffusion-limited MTO catalysts. This is simply what you would expect from a textbook in the Thiele modulus. Okay? Material characteristics have an effect on the hydrocarbon pool, and that's because we simply experience diffusion limitations. So this dual cycle schematic is very useful to understand what happens when you change the composition of the hydrocarbon pool from a material standpoint, from the feed standpoint, but also from the topology standpoint. This, I told you, is the industrial zeolite that's used for this chemistry. This is chabazite type topology. I'm going to use here SAPO34. This is a silico-aluminum phosphate. This is a cage window material. These windows are about 4 angstrom. And what is different about this zeolite is there is no steady state. I told you deactivation is a concern for us. How do you define reaction progress? How do you define how good a catalyst is? You define the catalyst, you define how good a catalyst is simply by using a turnover number. How many molecules of methanol make a hydrocarbon product before the catalyst deactivates? That's what you ask a catalyst to do. How much does a catalyst convert? A good catalyst is one that accomplishes more turnovers, and how fast does it do it? So I'm going to use the turnover number as a variable for reaction progress. There's no steady state. You see conversion go up as you make more and more chain carriers, then it deactivates. But with this trend in conversion, I see a very systematic trend in light olefin selectivity. I get more and more ethylene. This is also explained by this dual cycle schematic that I've been showing you. Very simply, I start from a cage window material which has mostly empty cages. I start propagating olefin and aromatic hydrocarbon pools, but this topology compels you to accumulate aromatics. Because once you make an aromatic, it cannot leave the pores of the zeolite. Essentially, the intracrystalline residence time is infinite. This cage will now only propagate the aromatic cycle. The topology compels you to make the hydrocarbon pool more and more aromatic. And as I make the hydrocarbon pool more and more aromatic, I keep seeing this monotonic trend in ethylene selectivity, and ultimately the catalyst deactivates. So this dual cycle schematic is very useful towards understanding how methanol to hydrocarbons chemistry proceeds. What it does not explain is how do I take these sorts of monocyclic species to these polycyclic species. There are many routes to do so, but there are some that are unique to methanol, and those are the ones that I'll try and highlight. How do I take a monocyclic aromatic, make a polycyclic? That's the question that got us interested. That's what torments us. That's what I'm interested in addressing. So I've already shown you that I can take dimethyl ether and do this on a cage window material. But if you've noticed, I've only been talking about dimethyl ether when I'm talking about methanol to hydrocarbons. Why haven't I been talking about methanol? Because methanol behaves slightly differently. So let me show you how methanol behaves instead of dimethyl ether. If I put methanol here now, not the dehydration product, this is what my product distribution looks like. It looks very different from what I showed you for dimethyl ether. If I compare methanol and dimethyl ether side by side, those differences will become apparent. There's no trend in ethylene selectivity with methanol. There is a very perceptible trend with dimethyl ether. If you look at the x-axis here, I see 1/5 of the turnovers when I use methanol. Methanol deactivates faster compared to dimethyl ether. When I use methanol, my conversion goes up faster. It comes down faster. It deactivates faster. It accelerates faster. Both methanol and dimethyl ether make hydrocarbon products, predominantly make C2 to C4 hydrocarbons. But when I make, of the hydrocarbons that I do make, I make more alkanes when I use methanol. And the difference between methanol and dimethyl ether is that you can make a stable product upon dehydrogenating methanol. Let me explain. Both methanol and dimethyl ether can react with protons to make surface methyls. We can evidence this very simply by spectroscopic means. Methanol by itself can act as a hydride donor. Methanol can give up its hydrogen. You see methane very early on in this catalysis. You see, especially at high pressures of methanol, you see methane as a primary product. You make hydroxymethyls, and these can, again, give up a hydrogen and make formaldehyde. This is what I mean that methanol can be dehydrogenated. Essentially, you do a disproportionation of methanol. You make formaldehyde, water, and methane, and you make formaldehyde. On the other hand, there is no equivalent of this. You can make methane, but there is no equivalent of this. You cannot desorb the species to make a gas phase product. This is an open catalytic sequence. If you think about it, methanol can be dehydrogenated to make formaldehyde. There's no equivalent for dimethyl ether. You cannot dehydrogenate dimethyl ether and make a stable gas phase molecule. Okay? So if formaldehyde is the key difference between methanol and dimethyl ether, how would it explain why our catalyst deactivates when I use methanol? How would it explain those trends that I showed you? Formaldehyde is a very reactive molecule. It reacts with olefins via something known as the Prince condensation reaction to make dienes. So if I take propylene, it reacts with formaldehyde to make butadiene. Butadiene rapidly makes aromatics. So when I have formaldehyde present, I already move towards the aromatic pool very rapidly. This is why I don't see that trend in ethylene selectivity, because methanol, when it makes formaldehyde, compels me to go towards an aromatic hydrocarbon pool. Formaldehyde can do electrophilic substitution reactions with aromatics, make these pendant hydroxyl groups, make these pendant alkyl groups. This is what ring closes to make bicyclic species. This is why I take the aromatics that I move and alkylate them and deactivate rapidly. So it makes dienes, which make the aromatic pool. It takes these aromatics and makes polycyclics. This is unique to methanol. In dimethyl ether, I see this gradual evolution in the hydrocarbon pool from olefinic to more and more aromatic because the topology compels me to do so. With methanol, because I have formaldehyde present, I right away go towards an aromatic hydrocarbon pool because I take olefins, I alkylate them, I make dienes which rapidly cyclize. So immediately I make aromatics. I don't see this trend in ethylene selectivity because my hydrocarbon pool is already dominated by aromatics. Of the aromatics that I do make, so I get fewer turnovers because when I make aromatics, I do electrophilic substitution, and I immediately convert them to polycyclics, or I convert them to polycyclics. So I get fewer turnovers when I use methanol. I accelerate faster because formaldehyde is a very reactive species. I decelerate faster because Formaldehyde alkylates my olefins or my aromatics and makes polycyclics. And I make more alkanes because anytime you make polycyclics, which have a carbon to hydrogen stoichiometry greater than half, anytime you make carbon-rich products or hydrogen-deficient products, you have to compensate that by making some species that are hydrogen-rich. So of the hydrocarbons that I do make, I make more alkanes to compensate for the fact that I made many more polycyclics, which are hydrogen-deficient. So the difference between methanol and dimethyl ether is that methanol can do transfer dehydrogenation, make formaldehyde. It's not the big debris that you see at the end of the reaction that causes deactivation. It's actually the smallest of these species that is responsible for deactivation, or a particular route for deactivation in this catalysis. And now the challenge to fixing what maddens us about this chemistry is simply removing formaldehyde. How do I remove one species in a mixture of many? I do so by adding a second catalytic function. Rare earth oxides have the ability to decompose aldehydes and ketones in mixtures of other alcohols or other hydrocarbons. So if you add a rare earth oxide, the data I'll show you this morning is yttrium oxide. If you add, you can do it with other rare earth oxides as well. So I'll show you an example. These are my data for both SAPO34 and its equivalent zeolite, which is SSE13. These are the data I've already shown you. I get acceleration and deceleration at the catalytic rate. When I add yttrium oxide, this is the second catalytic function that I've added, in interpellet mixtures with 100 micron length scales, I see higher lifetimes. I see slower initiation, slower deactivation. I see some CO early on in my catalytic turnovers. That's because that's when I make most of my formaldehyde. When I increase the intimacy of mixing, I see a longer lifetime. I see slower acceleration, slower deceleration. I see more CO. This addition of yttrium does not compromise the light olefin selectivity that I make. I still predominantly make light olefins. Because it happens in physical mixtures at micron length scales, it must be a gas phase molecule that communicates between the two catalytic functions. It cannot be any other reason. At micron length scales, only gas phase species can communicate. So the observed intimacy between methanol, between the zeolite and yttrium oxide implies a species formed at the zeolite site, we think formaldehyde, with deleterious effects on catalyst lifetime, which causes us to deactivate. Again, we think formaldehyde, which can leave these 4 angstrom windows in chabazite. It has to communicate between the gas phase, and the gas phase between the zeolite and yttrium oxide is rendered innocuous by yttrium oxide. So this is why rare earth oxides can enhance your catalytic lifetime. It's because they decompose the byproduct, which we don't want in this catalysis, which is formaldehyde. I don't have to do this simply by adding a second catalytic function. I can also do this by adding another gas phase reagent. I'm going to add hydrogen, and this is going to, again, remove my deactivation. If I add gas phase hydrogen, this is high pressure hydrogen, the catalytic lifetime now goes up orders of magnitude. This thing can keep running for weeks on end. This is now finding application in syngas to hydrocarbons catalysis. This is part of the reason why syngas to hydrocarbons catalysis works as efficiently as it does, because hydrogen removes the accelerants of catalyst deactivation. It removes formaldehyde, as I'll show you. It does not. You still get predominantly the same product distribution. You still make mostly C2 and C3 hydrocarbons like olefins. You still make them in olefin to paraffin ratios which exceed 95%. You still make mostly light olefins. It does not hydrogenate olefins very well. It does hydrogenate dienes. Zeolites are very poor hydrogenation catalysts. I have to drive the reaction by using a large hydrogen pressure, but they're very selective hydrogenation catalysts. So I can hydrogenate these accelerants of deactivation, formaldehyde dienes. I can actually measure this rate constant and show you that I can hydrogenate formaldehyde dienes much, much faster then I can hydrogenate olefins. So it stays as a selective MTO catalyst, but it removes the species that cause deactivation. And this is why syngas to hydrocarbons catalysis work, and this is another strategy to remove these accelerants of chain carrier deactivation. So let me summarize the first part of my talk. My goal was to show you that our efforts in understanding these complex hydrocarbon systems entail examining the mechanistic sequence in context of the dual cycle schematic or the hydrocarbon pool mechanism. It's the small species that you don't see because they're so reactive, not the debris that you see at the end that is responsible for deactivation. This simple schematic allows us to examine how product distributions would change in different materials as you change certain material characteristics. It allows us to understand how product distributions would change as you change topology. It allows us to understand how product distributions are changed when you change the composition of the feed. And it allows us to examine what causes deactivation and how to remove that. In this case, I've shown you two examples, one involving yttrium oxide or a rare earth oxide that removes formaldehyde, and the other involving the addition of high-pressure hydrogen because zeolites are selective, although you have to drive the reaction using high pressures of hydrogen. So I told you in my first example, my goal was to understand how to change the kinetic trajectory to prevent it from going down in side paths. In the second half of my talk, I'm going to take up a different example. I'm going to take a molecule which is hard to activate, and this is methane in this particular case, and my goal will shift not from selectivity, but to one where activity is the problem. It's a difficult molecule to activate, and it's going to bring forth significant thermodynamic and kinetic challenges. What I mean by that is methane activation is on an enthalpic volcano. Okay? On a per carbon basis, methane is the most stable hydrocarbon that we wish to make. That's possible. So what I mean by that is if you want to make products that are more valuable, longer chain paraffins, olefins, aromatics, you have to go up in enthalpy on a per carbon basis. You can do this oxidatively, but then the danger is that you over-oxidize, so there's some merit to doing this non-oxidatively, but you have to pay a penalty. There's an enthalpic penalty. If you take methane and you make these hydrocarbons, you make hydrogen, so the number of moles is higher on the right-hand side, and there's an entropic driver to doing so. So you have to use high temperatures to drive the reaction, but entropy helps you drive the reaction. So it's an uphill reaction, but you have to drive it with temperature. So enthalpically uphill, entropically downhill. And the example that I've chosen today is to make methane to aromatics. That's right at the top of that volcano, so these barriers will be significant. There'll be onerous kinetic and thermodynamic challenges, and I'm going to try and tease that out for you this morning. So I'm going to do this in context of this particular chemistry, methane going to aromatics, high temperatures to drive the reaction. It gets an equilibrium conversion of about 10%. This is what thermodynamics does. But I'm interested not just in asking how much does equilibrium limit my conversion, how does thermodynamics change my rate? Okay? Not just the conversion, how does thermodynamics change my rate? How does it change my rate as the reaction progresses? If I start from pure methane and I go towards equilibrium, how does my rate impact? That's what I'm going to try and do. I'm going to try and tease out the impact of thermodynamics on the catalytic function, on the catalytic rate, deconvolute them for you. I'll do this in context of a state-of-the-art catalyst. We are certainly not the first group to do this. Many, many groups around the world have done this. It's a molybdenum inside a ZSM5 catalyst. You always get about 67 to 70% benzene. You make about 90% selectivity to aromatics because you get some naphthenes. You make some light olefins, C2s, and almost everyone gets the same selectivity because we all can make a pre-catalyst for this. The state-of-the-art pre-catalyst for this is a molybdenum CSM5. You make this on high aluminum content materials because it allows you to make well-defined materials. I'll show you why you need high aluminum contents. You have to start with a Bronsted acidic zeolite. You exchange this with molybdenum, and then you make a molybdenum-5 catalyst. So how we've made it is following, it's unfortunately cutting out the references at the bottom, but how we make this is following precedents in the literature. It's a solid-state ion exchange. You make, we think, these molyoxidimers. This is why you need high aluminum content material, because it allows you at low molybdenum loadings, high aluminum content, allows you to make catalytic precursors that are well-defined in stoichiometry, well-defined in structure, and well-defined in oxygen to molybdenum ratio. So these are catalytic precursors. You can see them spectroscopically. These molyoxo bonds are quite accessible in the pre-catalyst spectroscopically. These are well-defined in stoichiometry, the exchange Bronsted acid sites. These are our data, the ones in red. We're following a precedent literature that I'm showing you here, which was done by using aluminum, NMR, and using hydrogen deuterium exchange, our data overlay. You replace one proton with one molybdenum in the catalytic precursor, and you can count the oxygen to molybdenum stoichiometry. Again, as I said, this is a pre-catalyst. When you activate this catalyst, it's not oxidic. You expose it to methane, and you simply see how the oxygen comes off. The oxygen comes off the catalyst in an induction period in this catalysis, and you make these carbides, and there's some carbon deposition. The catalytic function of this material is carbidic. It's a moly carbide that works as a catalyst. This is simply a pre-catalyst, but the oxygen is removed as CO and CO2, and you can count this, and it's always about 2.5 oxygens per molybdenum if you start with a high aluminum content material and low molybdenum loadings. So with this catalyst in hand, I'm going to try and answer two questions for you. Okay? The first, how do we deconvolute kinetic and thermodynamic contributors to rate? And I'll try and show you that this is the reaction network for this chemistry. After I have used this to benchmark my catalyst, after I figure out what the kinetic role is, then I will try and answer what torments us about this catalysis. I told you can only get about 10% conversion. What torments us is this thermodynamic path, thermodynamic trajectory, and then I'll try and remove these thermodynamic barriers to reaction. So first, let me show you. I have to find out what the reaction pathway is, and let me show you that this is indeed the reaction pathway. If you take a molybdenum ZSM5 catalyst and run it under the conditions that I've shown here, about 90% methane, this catalyst deactivates. You get this initial induction period, which is stoichiometric. You're carburizing the catalyst, and then the conversion decreases over a period of 2 days or so. The benzene rate decreases. You start seeing some change in selectivity, so the benzene rate decreases. You start seeing some change in selectivity. And it's this catalyst deactivation which we're going to use as an investigative tool. So catalyst deactivation in the first case was a problem. In this case, it will actually help us because I'm going to plot these data, selectivity versus conversion, slightly differently. So this is the benzene selectivity, C2 selectivity against plotted here. Now I'm going to take a fresh catalyst, load slightly less catalyst, and do this catalysis again. So I'm going to do the same reaction again. And this is what's going to help us show that this is the reaction network. I take a fresh catalyst. I load less of it. This is the behavior I see. I see the same, a continuation of the same behavior. The catalyst seems to follow the same trend. I'm going to do another experiment where I'm going to load less catalyst. I see a continuation of the same behavior. It seems to behave identically. How does a fresh catalyst behave identical to a partially deactivated catalyst? This is because this is true not only the way I'm showing you, it's also true like this. It's also true for every single C2 species. This is because the catalyst is deactivating non-selectively. When the catalyst is deactivating, it's just losing sites, but the sites that remain are identical. So it's simply losing sites, not the identity of the sites is not changing. And there's great utility in this because it gives me information as my catalyst is deactivating. In time, I'm getting essentially a spatial profile along the reactor. So this temporal evolution of the catalyst in deactivation is giving me information axially along the length of the bed. And now I can do this experiment again. We do it 4 times with 4 different samples, but now at much lower conversions, and allow the catalyst to really deactivate. And I see that when I go to very, very low conversions, this is my only primary product. I only have ethane as the primary product. Then I see ethylene, then I see acetylene. It's a series reaction network. Okay? This is the reaction network, and it's the primary product is only ethane. Can I verify this network? I can. I told you it's a highly reversible network. Thermodynamics will help me here. How do I use thermodynamics? I'm simply going to divide this reaction into 4 overall reactions, A, B, C, D, and I can measure all the products of the reaction. I can measure each of these species. These are gas phase species. And thermodynamics says that the reversibility of every step should be less than 1. I should be going downhill. The thermodynamics says the reversibility of each step should be less than 1. I can calculate this, for example, for step A. I simply know the gas phase composition of every species. I'm going to take all the data that I've shown you, and indeed, the reversibility of every step is less than 1. At least I haven't violated anything in thermodynamics. Okay? But I do have a problem. I've written the reaction as such. I've written methane with a stoichiometry of 6. This is the reversibility of step A. What if I wrote the reaction slightly differently? Stoichiometry is a construct, is arbitrary. What if I wrote the reaction like this? I get a different answer. My ZA has changed. Let me compare them side by side. They are not the same. In fact, my reversibility scales with the basis. It scales exponentially with the basis. I don't want to do my thermodynamics where my arbitrary choice of stoichiometry impacts my basis. I want an intrinsic reporter of the thermodynamics. I want a reporter based on elementary steps. We should do thermodynamics at the same level where we do kinetics. If we think of kinetics of elementary steps, we should also think of the kinetics of the thermodynamics of elementary steps. And I'm going to show you how in this particular example. Okay? Thermodynamics should also be done at elementary step levels. I'm going to do this because I know what the stoichiometry of an elementary step is. It's not arbitrary. And I'm going to relate that stoichiometry intrinsic to the reaction to the stoichiometry that I've written here using simply a stoichiometric number. Let's do this by example. Let me write this reaction again. Now I'm defining sigma. Now this is 6 divided by the number of carbons that are involved in these overall reactions in A, B, C, D. This number is 6 divided by the number of carbon atoms. And I'm interested in essentially what steps are involved in this, and if one of them is rate limiting and one of them is reversibility determinant. What elementary steps are involved in here? I can write this reaction again, and I can write in terms of the stoichiometric number of the elementary steps. So I'm going to start writing elementary steps with stoichiometry sigma star. So I can write step 1, reaction A, as 2 steps that look like this. And again, it's cutting the references out at the bottom, but following a precedent literature that I've highlighted here, we know that the first step is rate determining in this overall reaction A. What that means is that I can relate the reversibility of the elementary step, the first step, to that of gas phase reaction A, which I've already shown you. I've shown you the reversibilities of reaction A, B, C, D, and I can relate that now to the elementary step ZA1 by using the stoichiometric number here, 6 and 3, and I can calculate the reversibility of the elementary step in reaction A. I can do the same, so I can calculate reversibility at the level of elementary steps. I can do this for reaction B. I can do this for reaction C. In this case, it's quite straightforward. For reaction D, again, following a precedent literature, we think that the first step for taking acetylene to make dimerization of acetylene is rate limiting, and that's used to calculate the reversibility of step D. Now I have reversibility at the level of elementary steps, and I can again ask, is this downhill? It is indeed downhill for every single elementary step in this reaction network. Not only that, I learned something else. I learned that this is changing as the reaction progresses. The first 2 steps, methane, ethane, ethylene, are already equilibrated at conversions as little as 3%. They form an equilibrium mixture already at 3%. The only steps that are away from equilibrium are steps involving acetylene. Acetylene is the intermediate that is key and is the only step that determines my thermodynamic trajectory. I still want to ask something further. I want to find a number which tells me how much each step controls the thermodynamic trajectory. Essentially what I'm asking is, what is the degree of reversibility control? How much does each step control the thermodynamic trajectory? How much is each step displaced from equilibrium relative to all the other steps? This is simply how much it can be expressed in terms of delta G at any point in the reaction, divided by the sum of delta G of all the other steps as the reaction is progressing. This can be related to elementary step reversibilities, and it's simply proportional to the log of the reversibilities. This is how much each step controls the thermodynamic trajectory of the reaction network. It's a metric of thermodynamics. It is path independent. It simply depends how far each step is from equilibrium. It doesn't depend where it is in the reaction network. I can ask a different question. How much is the degree of rate control? Charlie Campbell has taught us how to do this. This can be done in context of rate constants. This is a kinetic parameter. In doing this work in methane DHA, we realized that we don't need to do this only in context of rate constants. We can also get to this parameter, the degree of rate control, using these sigmas that I've shown you, the stoichiometric numbers of the elementary steps and the reversibility of elementary steps. We can also come to this parameter using this information and the product. This is a kinetic parameter. It has a product of steps preceding it. What I mean by that is it has a term which includes the reversibility history of the preceding steps. So if I look at, this is path dependent. If I look at step C, for example, it recognizes that it comes third in the reaction network, not the first step. This is a path-dependent function. Also for step D, and all of them, of course, have to be less than 1. The steps controlling your rate and the steps controlling your reversibility do not have to be the same. In this particular example, it's very evident for the data that I've shown you. Methane activation is the rate-limiting step early on. It is the kinetically relevant step, but it does not have a significant influence on thermodynamics in this network. As the reaction proceeds, the rate-limiting step is changing, but the reversibility determining step and intermediate remains acetylene. Steps controlling the rate and your reversibility are different, and this changes along the reaction coordinate. Steps making acetylene become more and more kinetically relevant and thermodynamically relevant. Acetylene formation at the end becomes both kinetically and thermodynamically relevant. And if I combine all the steps involving acetylene, acetylene is the key intermediate that controls my approach to equilibrium, and it becomes the dominant kinetically relevant species at about 3.5% conversion. This is what allowed us to identify acetylene, even though it's formed in very low concentrations, as the key intermediate in this catalysis. So I promised to deconvolute kinetics and thermodynamics, and not just talk about thermodynamics as a limit on conversion, but I want to go back to the macroscopic variables. I've shown you this at the level of elementary steps. How does it relate to the macroscopic reaction that I've shown you? I have to again go to elementary steps. I'm going to think about kinetics. Rate, the net rate that I measure is the forward minus the reverse rate. I can write this as the forward rate times. This is essentially the reversibility that I've been talking to you about. I can do this also in context now of an overall reaction, not just simply for an elementary step. This is the kinetic parameter. This is the thermodynamic reversibility that I've talked to you about. I can write this now for the overall reaction or the macroscopic reaction as the forward rate and a product of reversibilities, elementary step reversibilities. This is the reversibility that the reaction experiences, the reverse rate to the forward rate. It is an effective reversibility. It is not the overall reversibility. The overall reversibility written on this arbitrary stoichiometry does not equal the same thing. The overall reversibility has to be moderated by a parameter, which is the sigma star. The sigma star acknowledges that we have steps in when you're growing carbon chains that have different stoichiometric numbers, and they have different driving forces for equilibrium. It's essentially a weighted average of the elementary step stoichiometric numbers times their degree of reversibility control. In this case, because acetylene is the key intermediate, it comes out to be about 2.5. Okay? It comes out to be 2.5, as I said, largely the degree of reversibility control is dominated by acetylene. It comes out to a number between 3 and 1.5 because acetylene is the intermediate that is controlling our reversibility. And the stoichiometry for this reaction perhaps should not be 6, but this 2.4, 2.5. This is what the reaction experiences at an elementary step. Okay, I promise to get you from kinetics and thermodynamics, parse them out. Now I have a benchmark kinetic catalyst. I know what the kinetics are doing. I know how much thermodynamics is influencing my rate. And I can take catalysts of various provenance, different molybdenum to aluminum ratios, low molybdenum, let them deactivate, let them start from different contact times, and I get the same rate every time because I understand how this catalyst operates. And now that I have addressed what kinetics and thermodynamics can do, I want to address how do I alleviate the equilibrium limitations. This is what I had promised to do. What maddens me here is thermodynamics, and I have to come and overcome that. So now that I know what my kinetic catalyst is capable of, I'm going to remove thermodynamics by adding a second catalytic function again, as I did in the first example. Okay. Okay, I'm going to add an adsorbent. So I'm going to carburize my catalyst, and I'm going to add a solid adsorbent. I'm going to add zirconium, elemental zirconium, after the catalyst is. An elemental zirconium can absorb hydrogen at that high a temperature, at 700 degrees, and make a zirconium hydride. You can go and see this in X-ray diffraction. You can go and see this in TPR experiments. Essentially, what I'm doing is now have a benchmark kinetic catalyst, and I'm alleviating this because I'm going to remove my product. I'm going to remove my hydrogen. It's going to form zirconium hydride. And now, actually, I'm not only going to remove my equilibrium limitations, but I'm also going to drive my reaction faster because I've removed all the thermodynamic constraints on how fast the reaction can go. It's going to go as fast as it can. It's going to be driven to its speed limit, which is the forward rate of reaction. So if I do this experiment, this is the benchmark catalyst, about 10% conversion, mostly aromatics. Without addition of zirconium, I can mix elemental zirconium in the form of interpellet mixtures. I get supra-equilibrium yield. I get 30% conversion. You can, of course, accelerate this by adding even more zirconium. This is a case study that we did where we added zirconium up front. Surprisingly, even with the addition of zirconium up front, you get a benefit. This is not an ideal plug flow reactor, otherwise you would not get this benefit if you add something to the front of the catalyst bed. If you add zirconium at the end of the bed, you again get a benefit. If you add zirconium in interpellet in the sandwich configurations, you again get a benefit. How do we understand how this catalysis is proceeding when I add a solid adsorbent? We use reaction transport models. We use essentially a dispersion term, a convection term, and a reaction term. I've already shown you how we can understand reaction in this system. We can non-dimensionalize this, again, from what we know from our undergraduate kinetics course, to get a Peclet number and a Dahm-Kohler number, and non-dimensionalize this. The Dahm-Kohler number is simply the rate of the reaction to the rate of the convection. I've already shown you how we can measure the rate of the reaction. The Peclet number is essentially how good a plug flow reactor this is. It's not an ideal plug flow reactor. I'm going to try and measure this. This is something we need independently. You can measure this by essentially adding a pulse and looking at the response of the dispersed pulse in the system. If you add hydrogen to the system, it disperses. Hydrogen has such a high self-diffusion coefficient that hydrogen, even though you think you have a plug flow reactor, it doesn't behave like a plug flow reactor. It has some back mixing. If you examine this, you do this experiment, you do a pulse, and you look at the dispersion of the pulse, you can assess the Peclet number. And now I think I have a reactor which I can examine mathematically in the context of this 1D model that I showed you. So let me try and see how it matches up with the data that I've shown you. If I have an ideal plug flow reactor, I would not see any benefit of adding zirconium at the end, and I would see no benefit in conversion. If I have a dispersed bed with a Peclet number of about 10, I would see hydrogen abstraction throughout the bed. I would see a benefit in conversion. If I have a Peclet number of about 1, I would see more hydrogen abstraction. I would see a benefit of about twofold in the conversion. This is not something that I'm making up. This is exactly what our Peclet number is. This is the model. These are the data. This is the model for this bed, for this bed, for these 5 configurations that I've shown you. This simple 1D model explains every set of data that I've shown you. It's a quantitative model. Now I can figure out how to optimally design this catalyst adsorbent configuration to alleviate my equilibrium limits. I can do so by leveraging this understanding that I have from my reaction transport model. I can change the length of the bed, see how long a bed would benefit. This is the baseline case that I've shown you. Now I can shorten the bed. I can lengthen the bed. In every case, my model gives quantitative information about how these reaction adsorption systems behave in the catalysis. So I hope I've shown you in my second example that in understanding in methane dehydroaromatization in a system network which is series and reversible, these concepts of reversibility should be understood not simply as a limit on equilibrium conversion, but at the same level that we understand kinetics, which is elementary steps. If you do your kinetics and thermodynamics on the level of elementary steps, you derive information which is new. You derive insight into steps limiting rate and reversibility in this chemistry. You get insight that steps that are limiting rate and reversibility do not have to be the same. You derive insight that acetylene, even though it's formed in very low concentration, is a key intermediate in this catalysis. You can use this information to inform alliance of concepts in reaction, transport, and thermodynamics to develop new systems that allow you to achieve super-equilibrium yield, drive the system to its kinetic limit. And this is all enabled by the rapid mobility of hydrogen in dispersed bed reactors. So this is all what my courage will get me to this point today. I am very grateful, very humbled, again, to represent this group and to have this honor from the North American Catalysis Society. Thank you so much. This is who we are. This is what we do. Thank you so much.
Thank you, Aditya, for a superb talk, and I thank all of you for your attention. And now we have a break, correct? Thank you again.